So we have two example problems here. Let's try this first one. They've both been on Smart Site. Okay. Go with this one. You have this old lamp, maybe your parents, uncle, something like that might remember it. It's an old bike lamp. It had other purposes, but it's common on bicycles used to be. And let's write down the reaction. Looks like a reaction is occurring to cause the lamp to burn. Calcium carbide, solid, plus water, H2O. Single-headed arrow here. Okay. And anybody know what, before I write the products, what kind of reaction this would be? It's a little tricky. It's going to end up being kind of almost a double replacement. In the sense that the calcium is going to go with the hydroxide of water. Remember, water is HOH. Okay, so the calcium will go with the hydroxide, and the hydrogen will go with the carbon. And it gives you the product C2H2. Okay? Oh, that's kind of like a double replacement. Okay, and let's see what we know. There's 100 grams of each. Now, each of these 100s, though, have 2 sig figs, not 1. Okay? We'll remember that in the end when we do our final kind of sig fig check. And then what do we want to know about the mass of ethylene? Okay, this has to be a limiting reactant problem. The reason is there's information given about more than one reactant that leads to moles. So we've got information about both of these. We can use either of these to find the mass. That means we have to do both to figure out which one gives us the correct chemical answer. So we'll try 2 different colors here first. The calcium carbide, let's start with that one. Okay, start with that one. And we have 100 grams of that. Again, we're finding mass. So I'm going to change this to moles as my first step. Molar mass of this from the periodic table, 64.10 grams. Now it's in moles. Now I want to do a molar ratio. But no, I haven't balanced this yet. I think I just need a 2 in front of the water. Okay. And now, I'm going to do this problem a little bit different than the one we did last time in class. I'll show you how, just so you can see something a little bit different. I'm going to moles of C2H2. I have 1 mole of CaC2. Okay, here's what's going to be a little bit different. I'm just going to stop at moles. I could have gone to grams, but just to see, if you stop at moles, it's going to be no different in your calculation. So I'm just going to stop at moles for the moment, 1.56 moles. Again, we'll figure out sig figs a little later. Okay. Now let's do the exact same, and remember this is C2H2. Exact same thing now, but we're going to do that for water, H2O. Going to start, it also started with 100 grams. We're going to use the molar mass of water to change to moles as our first step. And then there's 1 mole of C2H2 for every 2 moles of water. And this turns out to be, and again we'll just stop at moles instead of going to mass yet. We'll go to mass later. C2H2. Okay. All right. Which one, top or bottom, is our correct answer? It has to be the top one because it's the smaller answer. The smaller answer is given by the limiting reactant. So it's a smaller answer. Thus, the limiting reactant was CaC2, calcium carbide. The one that's in excess is water. Okay, now let's take our final step and change this to mass. Alright, so I'm going to take the 1.56. Again, we'll figure out sig figs in a minute. C2H2, that's moles. Let's go to mass. And it's 26.04 grams per mole from the periodic table. And that turns out to be about 40.6 grams C2H2. Alright, then we get a different color pen and figure out the sig figs, just so we got that all straight. Okay, this answer should have how many sig figs? Should be 2, because the 100 given originally in the question had 2 sig figs. So I'm looking really at 2 sig figs here. That means this has how many sig figs? Really only 2. So for the answer for part A, for part A, my answer is really 41 grams of C2H2. Alright, that's the first part. That was part A. Now we're at part B. Okay, for part B, what mass of the excess reactant remains after the reaction is complete? Okay, let's try this. So there's, here we start with the correct answer. So we can start with this mass, but I already know the moles, so I might as well just start with the moles, because I'm going there anyways. 1.56 moles. So yeah, I'm starting with the correct answer. I'm going to work backwards towards the limiting reactant. So I'm moving backwards towards the water. The problem is, or this is the one in excess, I mean, the water that was in excess, I didn't use all 100 of this, because it was excess. So I actually used a little less. I could have used actually 90 grams or 50 grams, I don't know. So what I'm going to do is back calculate and find out how much water did I actually use from the correct answer. Okay, so let's do that. So I got moles of this, and I want to go to water, so there's 2 moles of water for every 1 mole of C2H2. And then the grams of water, because I want to go to mass, 18.02 grams per mole. And this turns out to be 56.2 grams of water. We'll hold on to sig figs for just a second. 56.2, so that's the actual amount of water I used out of the 100. So there's about 40 something that I didn't use, it's extra. So part B wants us to find out the amount that remains. So this is the amount that I used. So what I need to do is go 100 minus 56.2. Okay? And so we'll hold on to sig figs for just a second. This is 43.8. Okay? And this is going to be grams remaining. This is what I did not use. Okay, the sig figs, let's get a different color to figure that one out. Okay, how many sig figs is this going to have first? I know I have 3 digits, but how many sig figs are there? Should be 2, because this had 2. I came originally from this answer. So 2, this has 2 really, so this has 2. Let's just underline that, so I remember. Now the original 100 had how many? Also 2. So now, if you're following my method, the error comes from the 100, which is in the tens position. So if I line that up, my error carries down to the tens position. So my answer will now have how many sig figs? 1. So what's my answer? It's 40. Yeah, I gotta round down because it's 43 and 44 rounds down to 40. So the answer is really 1 sig fig grams of water remaining or unused. And that's again because the error of the 100 is in the tens position. So you gotta go all the way back to the tens position, which is where the 4 is, so 40. You have amazing, great memory. You would have remembered we did this either the first or second day of class. I think the first day of class, I actually did this calculation to show you sig figs. So you would hopefully be freaking out slightly less right now. Okay, any questions on this problem? Was there one more part? Let's see. Oh yeah, there's one more part. So we'll do C if we're okay with part B. Cool. I've noticed whenever I don't do this calculation on the first day to practice sig figs, there's a big freak out moment right at this moment. But I'm glad that at least most of you feel better. Or you're being more secretive about it. Either way, it's cool. So, we found, they gave us the answer of 29.9 grams of ethylene produced. You're like, that's weird, because I calculated in part A 41. So what they're getting at here is this 29.9 that they're giving you is actually the amount gathered in a laboratory. And so they want us to do a percent yield question. Percent yield is 100% times the actual amount, or the amount given, divided by the amount calculated. 40.6, I'll just add a couple digits for now, we'll figure out the sig figs in a moment. This turns out to be 73.6%. Okay, let's check out the sig figs now. The 29.9 will have 3 as given, but the 40.6 from before just had 2. So really this should have 2, and it'll be 74%. Okay, cool. Any questions on that? Hopefully that part's cool. Easily pairing that percent yield with eliminating reactant column. By the way, some of you are on the stairs. There's lots of extra seats. You don't have to sit on the stairs if there's so many extra seats. There's probably 40 extra seats. So feel free to move while we're doing the next problem if you want. You can sit in a chair. It's okay. It's okay. All right. This one. For this problem, I have an overall reaction up above in blue, and then in black below that are what we call the consecutive reactions. And what I want to be able to do is manipulate mathematically the reactions in black, the consecutive reactions, in order to add up to what is my final answer, this one right here. Okay? So these need to add up to this one, and as they are right now, they don't. So let's work on that. Here. All right. Okay, first of all, what can be helpful sometimes is figuring out what's the intermediate. The intermediate is something that appears in the consecutive reactions, but not the overall. Let's move this down a little bit so you can see it better. Okay, what are some intermediates here? H2O doesn't appear up here, but it does down here, so that counts as intermediate. Okay, anything else? CO2 doesn't appear up here, but it does down here. So yeah, is that the only two? I think so. Okay, so those are my two intermediates. That means these must cancel as I add up the consecutive reactions. So there's two kind of methods we're going to take here. One is I can manipulate these so that these cancel, and the second is manipulate these so they match with what should be here. Usually I start with what I mentioned ladder, which is manipulate these so they match with this, and then I only move on to working with intermediates as my subsequent step. And that's my general way of solving this. There's other ways, of course. Okay, so what I'd like to do is find something down here, find something up here that matches down here, but only appears once in the consecutive. So what's here that only appears maybe once or so down here? Is there anything like that? The CO appears twice here. The H2 appears a couple times. The CH4 appears a couple times. The O2, is that okay? It appears once here and once here. That'll be an easy one to work with. It's easy to work with something that doesn't appear a lot. And here's why. Okay, let's make a special box here to symbolize O2. I'm going to use a couple different colors here. I must have 1/2 O2 in my answer. I must. So I'm going to change my consecutive answer here, and I'm going to multiply by what? I'm going to multiply by 1/4. Multiplying by 1/4 will change the 2 into a half. And those O2 is in the reactant, so I'm not going to flip the reaction or anything. Okay? And that'll make that one set. And now CH4 appears a lot, that'll be hard to work with. CO appears here and 2 other times, that's hard to work with. H2 appears a couple times, that'll be hard to work with as well. So now I'm going to check out the intermediate, see how I feel about those. I'm looking for an intermediate that doesn't appear too often. So for example, H2O appears here and only here. That's good. I want H2O to cancel. Let's work with H2O right now. So let's make a different color for H2O, or a different shape. I'll do an oval blue for H2O. Okay, I need H2O to cancel. My first reaction already has a multiplier of 1/4, so I'm not going to mess with my first reaction. I know my first reaction is correct, but I can mess with the third one. What can I multiply this third one by to cause the H2O to cancel? Times, there's 1/2 of this here, so I'm going to multiply by 1/2 here. So now, I'll have 1/2 H2O in the first reaction in the products, in the last reaction in the reactants. They're going to cancel when I add them. So now my first and my third reaction are pretty set. Let's work with my next intermediate, CO2. We'll come up with a different color for that one. We'll do brown, and I need a different shape. We'll do, yeah. You want to multiply which one? The 1/2? Okay, he's asking if I need to multiply the third reaction by -1/2. No, because that'll put H2O on the same side and it'll just add to each other. Right now they're on opposite sides of the algebraic equation, like plus x here, and they'll just cancel. Yeah. So I want to leave it as is. I don't want to flip the third reaction. Good. But let's see what happens here. Okay, CO2, let's make that a sheet. And there's CO2 here. Okay, so that's a brown sheet. Now, I have 1/4 CO2 there. What do I want to multiply my second reaction by to cancel out CO2? Times -1/4. Why? Because a plus 1/4 will cancel with a negative. The negative really means I'm flipping the reaction, but it'll cause that term to cancel. So I'm going to get rid of my CO2, I'm going to get rid of the H2O. I have a multiplier for all 3 reactions. I'm actually done. Now you can check your answer. Once you have a multiplier for every reaction, you're actually done. But you can check. So right now, if you added these 3 reactions, they would add up to this one. But I know you don't believe me, so I will prove it to you. We know O2 adds up. Let's check CH4. What's 1/4, and remember this is flipped, plus another quarter plus a half? What does that add to? 1. Check. Let's try CO. Where is it? Oh, it's here. What does a half over here and a half here? Oh, that's 1. That'll work. And H2 is going to be, this will flip, so it's a half plus 3 halves. What's that? 2. That works. Check. They all add up. So if you do your work right initially, it'll always work. You got to multiply for each. You know how to add these. That's the purpose. How do I add these to add up to the total one? Again, this is something you'll start to see in chapter 5, but you're going to see this a lot in 2b and 2c. It's something called Hess's law, and then later something called like reaction mechanisms. You'll see. Okay, we're cool with that. This I would consider a medium difficult question. So if you feel pretty good at this, you're doing pretty well. All right. Let's see where we are here. Oh my goodness, it's a week before the exam. 4 or 5 days we need to start studying. I will post, I haven't posted some of the practice exams and stats for you. I'll post 2 practice exams on the Smart site. What else? I will try to schedule a review on the potentially the Sunday before. So this Sunday, I'll let you know by Smart site when that's going to be precisely. You don't have to come. Okay, the review is optional. I'll actually try to record it and post it online. So if you don't come, it's fine. It's totally optional, but it'll just be a review. You'll come with questions. I'll just answer your questions. They'll be informed. Okay, let's continue on now with Words Chapter 5. Really Section 5.2. And that's page 33 in the reader and page 158 in the textbook. Okay, what's the deal on this stuff? Gotta introduce a little game we call Will It Precipitate? PBT is for precipitate. Will it precipitate? Precipitate is something that comes out of the current state it's already in as a solid. So for example, a solid in a liquid via reaction would be a precipitate, or even snow. Snow in air would also be considered a precipitate. So there's something called solubility rules. We'll give these to you on the exam. And the purpose of this is to figure out, is something going to be a precipitate as a product? Or sometimes as a reactant. That means, will it be a solid or will it be aqueous? So this is a great way to tell if something will be solid or aqueous. There's not going to be any math here, which will cause this to be usually work. But 99% of the time, these solubility rules will be great. In Chem 2B, lucky you, you're going to put math, crazy math, to all this, and you'll be able to actually calculate this stuff. So I know you're looking super excited for that. Will it precipitate? So I'll give these to you. What's typed here will be on the exam 1, 2, and the final. AQ means aqueous, S means solid, of course. So AQ means no precipitate, solid means precipitate. Okay? Or AQ also means soluble or mostly soluble, solid or precipitate means insoluble, or slightly soluble. Okay, this is a little bit different than the way it's written on the text, but I think we can survive. Okay, let's do a couple examples just so you can get some practice at using this. Okay, and this is all for the purpose of figuring out state symbols. That'll be really helpful to us. So let's say I have something like aluminum nitrate. Take a second, don't say it out loud. I want to figure out, will it precipitate? So I need to know what that state symbol will be in that parentheses. You can talk to your neighbor, think about it for a moment, and then I'll ask everybody. And we're going to go through a couple of these. So I'll put a couple up here just so you can think ahead if you want to. Alright, that's good enough. First one, will it precipitate, yes or no? No, so it'll be soluble or aqueous according to which bullet, 1 through 5, which one? 1, according to the first bullet, that one's aqueous. It will not precipitate, it is either soluble or mostly soluble. Okay, let's take a look at the next one. Will it precipitate, yes or no? I think I'm going to have to go no here. A sulfate, that's a sulfate. You usually think it's going to be aqueous, but there's an exception with all these ions, so it's actually a solid. Okay, so make sure you check those exceptions. What's that? Explain that again. We're looking at the third bullet, is the one that applies. It's because we have a sulfate. The sulfates are usually aqueous. But there's an exception, and the exception means the opposite. So if there's barium, it's actually a solid, not an aqueous. Okay. Okay, let's do the next one. Will it precipitate, yes or no? What bullet are you looking at? Okay, some of you are looking at bullet 1. Is there any other bullets? 5. 1 and 5. Because I have a chromate and I also have a group 1. Potassium is a group 1 compound, or ion, really. So, potassium chromate, when you have 2, see this, it says except above rules. So rule 1 trumps rule 5, because rule 1 is above rule 5. So really these are kind of in trumping order. This is aqueous. Because of the potassium, the chromate does not overcome the potassium. Okay, next. Will it precipitate, yes or no? I think yes, according to what bullet? Bullet 5. You see the carbonate right there? And I don't think any of the exceptions will overrule that carbonate with the magnesium solid. Okay, what do you do with the last one? Yeah, it's just water, it's a liquid, you don't even need this stuff. Okay, so don't be crazy. If you know it's a liquid, you don't need to use this crazy stuff, it doesn't even apply. Okay, this applies for ionic compounds only. Ionic compounds only, that wouldn't apply really to water. Okay, so this has a specific purpose, it doesn't work for every possible compound in the universe. The third one, the potassium chromate. Potassium chromate, you see potassium for group 1 here. Group 1, that's the first column in the periodic table. Chromate though here. Well, chromate says except above rules. And this is above rule, so this rule trumps. And group 1s are soluble, so it's aqueous. Okay. Bullet 4, what does that mean? Hydroxides and sulfides. So a hydroxide for group 4 is this. A sulfide would be this. 2 minus, yeah. Except above rules. So K2S would be what? Aqueous. Or group 2 sulfides. This would be what? Also aqueous, because a group 2 sulfide is an exception. But, like this is not a group 2 sulfide, so I'd probably put a solid there. Is that okay? Okay, that's how I use bullet 4. All these be bullet 4. Okay, so you gotta get used to the exceptions, but if you follow the rules, you're cool. It's okay. So we needed to learn that in order to do what's next. So we're going to use the solubility rules quite a bit. But first we have to figure out, or it leads us to this, which is the Net Ionic Equations. And you'll see a flowchart like this one on page 34 of the reader. We want to write Net Ionic Equations. Why is that? What's the big deal about this stuff? A Net Ionic Equation is the reaction that only includes the participants of the reaction, which is interesting to us chemically because we get to see what actually is reacting. That's why we like it. It's a removal of what we call a spectator ion or spectator ion. There could be multiple spectator ions. They have a role in the reaction to balance the charge, but they're not involved in the chemistry of the reaction otherwise. So we remove those kind of things, and we get down to the core of the reaction, and that's why it's interesting to us. And so that core of the reaction with actual participants is called the Net Ionic Equation, or the Net Ionic Reaction. And so we want to know how to write that. There's 3 steps in my method here. Step 1, write the reaction out and balance it, just like we've done in chapter 4. Is it a double replacement? Is it a single replacement? What is it? Write that thing out and balance it. That's step 1. Step 2, you figure out all state symbols. So all state symbols. How do you do that? you use the solubility rules that we just did for any ionic compound. So we did these solubility rules. That's one way to figure out the state symbols. And the other is general information. What's that garbage? That's what we ended class with last time on the bottom of page 33. So all this stuff that you see right here is the bottom of page 33 in your reader. That's standard conditions or your general information. Sometimes you need to know, like water is a liquid, so you know to put an L after water. So use either the solubility rules or general information from your standard conditions to figure out state symbols. And then your final last step is to write the Net Ionic Equation. And what you need to do that is basically you're canceling out or removing all the spectator ions. To do that, you need to know a little bit about electrolytes, which we also covered last time. That crazy stuff is also in your reader. You need to be able to tell the difference between a strong and a weak electrolyte. That's page 32 of the reader. And we also ended class last time with that. So knowing electrolytes, you separate everything out into an ion. So would that be, if it separates into ions, is that a strong or a weak electrolyte? That's a strong. So all strong electrolytes you separate out into ions, and you cancel anything that you see on both sides. Okay? This is kind of like a little math, cancel what you see on both sides. Yeah. I don't see you, but go ahead and ask me. Oh, what did I do? Oh yeah, 83. 83 is better. Should write 83 there. I'll wipe that out later. Yeah. 1 and 4 is also true, but really I should have said it. Anything, once it gets too big, the nucleus becomes unstable, and then protons and neutrons cannot hold together in that nucleus, and it starts to decay. Alright. So let's try this. Let's try to write a Net Ionic Equation so that we can figure out what's really going on in a reaction. You're going to see I'll always follow those 3 steps. Try this first one. So nicely I gave you the state symbols. Let's write the products. The products are, this is double replacement, so sodium chloride and HOH, which is also known as water. So I write out my double replacement. The state symbols for the first 2 are done for me. I don't even have to think about those. Water, you know, is liquid. So we know that one just from general standard conditions. And now let's pop up the solubility rules. I don't know where they are. I must have ate them. Oh, here it is. Okay. Sodium chloride. Aqueous or solid? Aqueous from bullet 1 and 2. Bullet 1 tells me sodium, group 1 is aqueous. Bullet 2 tells me that a halide, chlorine, or chloride is aqueous. So either bullet you use, you get aqueous for this one. AQ. And it's balanced. So we got it written, we've got it balanced. That's step 1. We got the state symbols, that's step 2. Now let's do our final step, step 3, and that is figure out what's an electrolyte. Let me zoom in for this part. Okay. Some of this I'll have to kind of tip my hat to you. The first one I'll let you know is a strong acid. Okay? If it's a strong acid, is it a strong electrolyte? Yes. The next one, is that a strong electrolyte? Yeah, it's an aqueous ion. It's also a strong base, but you didn't need to know that. It's aqueous ionic, it's a strong electrolyte. How about the next one? Strong electrolyte? Yes, it's an aqueous ionic. It's a strong electrolyte. Again, I'm referring to page 32 here in your reader. How about this one? No, because it's a liquid. Liquids are not strong electrolytes. So what does that mean? Electrolytes ionize. So you would write H plus and Cl minus, and sodium plus and OH minus, and sodium plus and Cl minus. But I'm not going to do that for water because it's not a strong electrolyte. And now you just cancel stuff that appears the same on both sides, and that would be sodium and chlorine. The H plus can't cancel because it's not on both sides. OH minus, same. Water, same. Not on both sides. So the final reaction is H plus plus OH minus goes to H2O liquid. And you'll notice here something that happened. I need to put my state symbols in for these. Ions are always what state? Aqueous. Yeah, I told you this last time. Ions are always aqueous, and they came from aqueous compounds. So hopefully that makes sense. So this is the reaction that's actually occurring. It's called the Net Ionic Equation. Let's try the next one. Again, a double replacement. Let's do step 1, write the reaction in balance. So I've got KNO3, and I've got H2CO3. Okay. Now, that's step 1. It's balanced. Oh, good. It's written, it's balanced, we're good. Step 2, state symbols. I luckily have the state symbols for the first two. For this next one, KNO3, what is it? It's aqueous according to what bullet? 1. It has a nitrate and it has a group 1. Crazy aqueous. Okay? AQ. Now, I'm going to also introduce a new concept. It's not really a new concept, it's just a thing. I'm going to introduce a thing. I forgot where this is in the reader, but it's in the reader and the textbook. I cannot remember. Oh, it's in, I'll just tell you, but if you want to look later, bottom of page 36. This compound in particular, carbonic acid, is not stable. If you ever see carbonic acid, it reacts immediately to form the following. And this is something you'd have to remember. I think by looking at the compound, hopefully it's not too crazy. It forms H2O and CO2 immediately. It's really at equilibrium, but this is the favored side of the equilibrium. So you need to remember that. If you see carbonic acid, it forms CO2 and H2O. And this is if you ever in high school, no, probably elementary school, made a volcano and you put vinegar and baking soda, that's this. You make carbonic acid, it forms CO2, and that's the bubbling. That is your volcano. Okay, so let's do state symbols now. That's aqueous. Water, we know that one. It's a liquid. CO2, what's that? It's a gas. Breathe it out. You exhale it. Okay. All right. Now we're on to step 3. Let's figure out what's a good electrolyte. This, I'll let you know, is a strong acid. Is that a good electrolyte? Yeah, let's write this one out. H plus plus NO3 minus. How about this one? Yeah, it's aqueous ionic. It's an ionic compound, it's aqueous, that's a good electrolyte. This one? Yes, aqueous ionic compound. It's aqueous and it's ionic. Remember, it's ionic if it has a metal in it. So you're looking for a metal. Potassium's the metal. Water's not. How about CO2? No, why not? It's a gas. Gases are not good electrolytes. So for strong electrolytes only, I'm separating that into ions. That's by definition what electrolytes do. They separate out into ions. And let's see what cancels. K plus is on both sides. NO3 is on both sides. That's it, I think. So here, we get a H plus, the ion's aqueous. We get HCO3 minus, that's aqueous. And then we have H2O, liquid, plus CO2, gas. Okay? Any questions on that one? Yeah.
How come the second one with the potassium and the hydrogen carbonate is not separate the hydrogen and carbonate?
why don't we separate the hydrogen here? You're going to learn momentarily, but this is a weak acid. Yeah, that's why. And weak acids are not strong electrons. I'll teach you that momentarily. We won't do the last one. You can do it at home for fun if you want. There's some YouTube action. You want to see that? Okay, let's do a little bit more, then we'll take a break. This is section 3, which is page 162 of the textbook, and the reader's bottom page 34. Section 3. This is about acids and bases, which is what we're wondering about. An acid, I already told you, is something, as far as we'll typically see in Chem 2A, something that has an H in front. So it's H blank. For example, HCl, hydrochloric acid, H2SO4, sulfuric acid, etc. Those are good acids. There's also, this would be another acid, acetic acid. You'll see sometimes when you take OChem, they write this differently. How do they write this in write it like that. CH2CO2H, like this. So this is an acid, just the OChem way of writing, put the H in back. So you won't have to worry about that now, but in case you were curious. Acids are essentially H plus donors. What does that mean? It provides an H plus to the reaction, or loses that hydrogen that's in the front. The acidic hydrogen. It donates it. The more it donates it, the stronger the acid. So if it donates, every molecule donates an H plus, that's a really strong acid. If 5% of the molecules donate an H plus, that's a weak acid. Okay? That's how you tell the difference between a strong acid and weak acid. I'll be more specific in a moment after we do bases. So that's acids, so this is section 3. Bases. Base, got down here. A base would be a little bit different, like KOH would be a base. It's usually something that has a hydroxide polyatomic ion attached to it. So this hydroxide would symbolize a base typically for us. Let's do another one. Strontium hydroxide, that's a base. There's also ammonium hydroxide, that's a base. The problem is, sometimes bases are less recognizable. So another way to write this, if you remove the water from it, would be NH3 ammonia. That's a base. It's ammonium hydroxide, but just written a little bit differently, without the water group there. So these are all bases. Usually you recognize them by the hydroxide group. So it must be a metal with a hydroxide. So thus, this is not a base. This is not a hydroxide, that's why. It's not a polyatomic hydroxide chemically. This, with a non-metal and what looks like a hydroxide, is actually an acid. Okay, so don't confuse. It must be a metal with a hydroxide. Okay, so these are hydroxide donors. It's a definition of a base. There's a lot of definitions of acids and bases, and you'll get into that in Chem 2B. Now, you get to learn a new reaction. An acid plus a base goes to a salt plus water. Okay? Acid plus a base goes to salt plus water. We call this a neutralization reaction. Okay? Neutralization reaction. You're wondering, what does a neutralization reaction look like? Glad you asked, because we already did one. I just didn't tell you. Right here. An acid plus a base goes to a salt, salt means ionic, plus water. And the net ionic equation will almost always be this. So that's why we did this reaction in particular. Okay? Acid plus a base goes to salt plus water. It's a neutralization. So neutralization is a subset of what? Of what kind of reaction? A double replacement. It is a type of double replacement reaction, which is what this is, a double replacement.
Can't water be an acid or a base?
Yes, that's correct. Question was, can water be an acid or base? That's correct. You can act as both, but in both cases it's weak. So it's called amphoteric, and you'll find that out when you get into Chem 2B. So, but because it acts as both, really we consider it neutral. Now it doesn't have to be neutral as far as an acid or a base to be amphoteric, but water is one of those, or is the one that is both neutral and can act as an acid or a base. Again, exciting 2B material to look forward to. Okay. Now, I want to cover one more thing, and we'll take a break. So you probably are wondering, how do I tell the difference between a strong acid and weak acid? Because I need to know that to do a number of things, especially determining electrolytes. What's a good electrolyte? So what I'm going to do, I'm going to try to set a world record here. I want to teach you how to tell the difference between a strong and a weak acid and base. I want to try to do that in about 5 seconds. Okay? Any compound you see in the world. Okay? If it is a strong acid or a strong base, it's on this table. If it's not, it's weak. Good. I think that was about 5 seconds. If it's on the table, it's strong. If it's not, it's weak. There are very few exceptions to that statement. Okay? This table is in your textbook and in your reader. In the textbook, it's on page 163, and the reader is page 35. The textbook does not include this chloric acid, which I think is a reasonable one to include. It's one of the weaker of the strongs. So it's like a super buff guy, but the guy who does not win World's Strongest Man on ESPN2. Okay? So it's a weaker of the strongs.